Alright everyone, we're here for 8.4. Looking at our learning goal, we're actually going to focus more so on bases for this video, so we want to go ahead and get right into it so we don't have to spend a whole lot of time. Again, I do apologize that the last one was a little bit longer than expected, but let's go ahead and start from here. Our goal, of course, by the end, we want you to be able to determine the pOH or hydrogen ion concentration given base solution and related to the base's strength. Now, Arrhenius, according to Arrhenius, the definition for a base, it releases hydroxide ion concentrations. Bronsted-Lowry says that it's the substance that accepts protons. Usually going to have a pH that's greater than 7. And ionic compounds containing hydroxides are usually the strong ones. So lithium, sodium, potassium hydroxide, calcium hydroxide, and so forth. Now, to find the pOH, we're actually going to just take the negative log of the hydroxide ion concentration. And if we need to find the pH from that, pH would be 14 minus the pOH. Straightforward. That part we kind of reviewed. Now, we want to look at an example. It says calculate the pH of a 1.0 times 10 to the negative third molar solution of sodium hydroxide. Now, if we need to know the pH of this, again on the previous slide, we said that the pH is equivalent to pH is equal to 14 minus pOH. So let's find the pOH. We're going to get the negative log of our concentration, which is 1.0 times 10 to the negative third. This is going to give us 3. That's our pOH. So to figure out the pH, we're going to do 14 minus that. So 14 minus 3 gives us a pH of, oops, it's not an H, 11. I erased a little too much, it's okay. pH of 11, okay? Now, this is the basic idea for something that we're dealing with, just to start off. Now notice we were dealing with sodium hydroxide. In this case, we were only dealing with one hydroxide that was being released. Let's look at another example. We have calcium hydroxide. Now, calcium hydroxide, we know the formula is CaOH2. So because of that, that means for every one calcium, we have 2 hydroxides. So we're going to end up having to double this concentration. So to find the pH, we're going to do the same exact thing, but this time we have to double this concentration. So just get negative log of 2 times that value, which is going to be 2.0 times 10 to the negative third. Now, this gives us 0.0. Sorry, let me make sure I haven't gone crazy. That gives me, oh, nope, that actually gives me the value of 2.69. Sorry, I almost made a little mistake there. 2.69. That's the pOH. So I'm going to do 14 minus 2.69 to get 11.31 as my pH. Okay? Now, still the same idea, but again, this time we just started with the pOH and worked our way to the actual pH value. I'll go ahead and clear the slide. And they got approximately the same. Now, when we write the equilibrium expression for a weak base using Kb, we want to remember something. Usually that means we're going to start the reaction with our conjugate base, what we normally would think of as a conjugate base. It's going to receive the hydrogen from water, water in this case acting as the acid, to form this. Now, because of this, we actually know that the reaction is actually going to stay more on the left. So the value is going to be fairly small. Now, we're going to do the same type of idea of what we dealt with in the previous example. So you notice I'm reiterating the pH of the solution for weak bases are very similar to those for weak acids. Kw still equals out to the same. It's going to be the hydrogen ion concentration times the hydroxide ion concentration should equal out at 25 degrees Celsius to 1.0 times 10 to the negative 14. Because we understand that relationship, we know that 14 minus the pOH will give us our pH. So let's look at an example right here. We have a 2.0 molar ammonia solution. Now, it already gives us that we have a Kb value of 1.8. So let's look at our reaction, our overall actual reaction. It's going to be NH3 plus H2O is going to produce what? Well, if this is the acid, it's going to donate. So we're going to get NH4 plus OH. Now, knowing that piece of information, it's ice time. So ice table, I know it's 2.0 molar. We know that this one's going to be constant. This is going to be 0, 0 starting out. What's the change? From this side to that, X, X. So that means 2.0 minus X, X, X. Plugging it in, we're going to solve and get X squared over 2.0 minus X equals 1.8 times 10 to the negative fifth. So we know that this basically cancels out because it's a weak base. So again, weak is not going to cause too much of an issue. Once we've solved through this part, we've gotten through the habit. So my hope is that you will come out with that X is going to be equal to 0.006. We're going to find the negative log of that. Negative log of 0.006. This is going to give us our POH, which is approximately 2.22. That's the POH. So 14 minus 2.22 equals 11.78, which is our pH value. Now, that was a good amount of work that we had to do there, but my hope is that you're starting to get the idea of how this works. What are the major species, just like we did before. Once we know the major species, going through, writing out the equation, and seeing how it's going to work from there. 11.78 being my final. Now, that's actually the end of this little section. It's very short, but it's based on what we had for the previous section for weak acids. So it's using the same concepts over and over. You're going to see these problems in class, and my hope is that you are prepared for them. Now, go ahead, rate yourself, say where you are. My hope is we've moved you closer and closer to that 3.0 level, and with practice, we can get you to master this concept. We're going to end it there, and I will see you all tomorrow.